Welcome back to Cricket Aviation. My name is Jim Payne, and I'm very excited about this video because in this video I get to reveal what engine selection I have made for the CriCri. I'm going to reveal the engine. We're going to discuss the pros and cons of using that engine on a CriCri. If you're actually interested in watching a video of this engine running, I'm going to save that for another video. It'll be released almost immediately after this video, but I'm going to dedicate this one to the CriCri, whereas the other video will be more dedicated to the engine itself. So please like the video, subscribe to the channel, and remember to subscribe to Instagram or Facebook. The links are in the description, so stick around and I'll reveal the engine choice. So here it is, the King Tech K100 turboprop. This is what I'm going to be using on my CriCri. This is 17 3/4 horsepower, 2-stage turbine that I think will work quite well on a CriCri. So we're going to start out by talking about the pros of this engine selection. And number one, probably at the top of my list, is that it sounds like this. So the second pro on that list would be the fact that it's smooth power. For me, you know, not using a two-stroke, not using a piston engine, having a smooth power either via a jet engine or electric power is in my opinion the ideal engine choice for me. I would prefer not to go the two-stroke route. There's nothing wrong with it. It's just the shaking, the vibration, that's not a good flying experience to me. And I thought, well, since my goal is to transition to electric power, I really think that's the future of the CriCri. I thought making a gas-powered version of the CriCri on my way to electric power would be a great option. It gives me the ability to make fuel tanks and actually have a gas-powered CriCri like it was originally intended. So, smooth power for me with having a turboprop allows me to just have zero vibration. It simplifies the construction of the engine mounts. The CriCri has a very complex method of handling the vibrations from two-stroke that it does very, very well. But this will simplify the installation of this engine, at least from the engine mount perspective. So that's probably the second reason. Now the third reason is that this is a very high-tech engine. Even though, if you're familiar with what this comes from the giant scale RC environment. This is used a lot of times on the Pilatus PC-21. It's very popular for that. And so the fact that we've got an engine here that has a full computer-controlled FADEC system, and if you're not familiar with that, it basically just means that this is a completely computer-controlled engine-managed system. It's basically push-start. You push the button, it starts. It will automatically restart. It's basically just turn it off with the flip of a switch. There's nothing that I have to manage on this engine that it doesn't manage itself. It manages all of its own temperatures. It's got full data logging, so that it will actually log all of the parameters that it is monitoring while the engine's running into a log that I can go back at a later time and actually look at how the engine's performing. Am I seeing any trends that are different? Are the temperatures rising? Some of those can indicate maybe it's due for a rebuild, or that bearings need to be replaced, those type of things. So from a pure aviation perspective, the technology that is built into this engine is something that you would only get from very, very high-end engines in aviation. So this is a huge step up from a two-stroke, for example, on what I could have for engine management capabilities on a two-stroke. So the other thing that's really cool about this engine is it comes with a ground support unit, GSU they call it. And what it is it's this touch screen here. I haven't actually stuck to the bottom of this, but it's this small touch screen that comes with it that allows you to monitor the engine from the ground. It's intended that you could have this on a bench here like I have here. You can actually have an LCD touchscreen display that shows you the RPM, all the temperatures, the battery voltages, everything that you would want to monitor on this engine while it's running is available on that touchscreen device. It also tells you the status of the engine, if it's in restart mode, what the throttle position is, those type of things. And what's cool about that little screen is that little screen I can mount right inside the airplane, and I have all of the instrumentation that I would need for any engine right there on this little touchscreen display. So having a full engine management system and having all of the instrumentation basically built into this one device that's part of the engine is in me a big benefit for the CriCri. I'm not going to have to add any additional instrumentation for temperatures or for battery voltages or RPM or anything really. It's all pre-packaged, all built together. So now let's talk about the negative things about using this engine selection. Probably on the top of the list is going to be the fact that this is basically designed for the RC environment. So I'm using an RC remote control type of engine on a real airplane. And that can be a little bit of a negative because the reliability sometimes isn't there. Although, you know, guys have been using 3W and ZDZ and Desert Aircraft type of two-stroke engines on the CriCri, and a lot of people have switched to that because things like the JPX aren't available, although Solo 210 I believe still is available through Hearth. But that's a single-cylinder two-stroke engine that is just it's a lot of shaking going on in you know, using a two-stroke engine like that. I believe some of the twin-cylinder two-stroke engines that are the giant scale RC equivalent are probably a little bit lighter on the vibration. So you know, going that route might be a better option. But again, we're dealing with engines that are not designed to be on an aircraft, a man-carrying aircraft. So, you know, do you have to worry about crankshaft braking on a two-stroke, for example, if you go with one of the giant scale ones? Do I have to worry about the reliability of this? I think when I look at this compared to the other giant scale RC options, I believe this is going to be far more reliable than, say, an equivalent two-stroke in horsepower. The great thing about having an engine that's a jet engine is you don't have all of the fuel issues and air mixture issues that you have to worry about on a lot of other engines. You basically, once you light a turbine engine, it will, as long as you're providing it fuel, it will keep running itself. So I think reliability-wise, on a flight-by-flight basis, I think I'm much more less likely to have an engine quit, for example, because a two-stroke carburetor you know, fouled or the mixture wasn't right or something like that. I'm not going to have to worry about some of those issues. But there's long-term issues with using RC jet engines. For example, RC jet engines require a lot of maintenance. And what I mean by that is these have bearings inside of them that have to be replaced every 25 hours. And that's true for this turboprop also, because this is a turbine engine connected to a gearbox that then is turning a propeller. So, you know, again, we've got issues with the fact that we do have to have a maintenance that has to be done on these every 25 hours. Now, this CriCri is not going to be a high-hour aircraft. This is not going to be a cross-country aircraft. I'm building this basically as an air show aircraft, or I'm building it as a stay within 5 miles of the airport type of aircraft. So I'm not too worried about the reliability on this, because I think it's as good as or better than any other option that I could select. Now, possibly if I went with a Solo 210, or I had a JPX or one of those other engines that was designed for a paramotor, for example, where the reliability is really kind of inherently built into it to be a man-carrying engine, I could possibly feel better if I had, an engine like that. But I think this is going to be good enough for me, especially for what this is intended to do. I may switch, like I said, at some point to electric power, so having this as an interim is fine, even if I don't put huge hours onto it. So if you watch the other jet-powered CriCri video that I did, where I discussed the pros and cons of using a jet engine, for example, on a CriCri, and mentioned that it wasn't something that you could really do in the United States because of the fuel requirements, you're probably looking at this going, Jim, you've got a jet engine there that's connected to a gearbox that's turning a propeller. How is that any different than having a pure jet engine, and why not just use the jet engine? Why have all this other stuff on here that you don't need? And here's the big reason. And many of you probably already know this, but for those of you who don't, a propeller is much more efficient at producing thrust at lower speeds than a pure jet engine is. And so if you think about it, most of the aircraft that you see out there, the higher speed aircraft are jet, the lower speed aircraft are piston engine with a propeller, and then you got that in-between stage that is a lot of times turboprop. And the reason that you have this variation and why everything just isn't jet engines is because at lower speeds, jets use a tremendous amount of fuel compared to a piston engine. Jets are great because at higher speeds, they continuously create relatively the same thrust that they create on the ground in static configuration, whereas a propeller will create a lot of thrust on the ground in static configuration, but then when you start flying it through the air, the faster and faster the airplane goes, the less and less thrust that the propeller produces. And so you get to a point speed-wise where you end up with enough drag going forward with the aircraft and the reduced thrust by the propeller that you reach a speed where your thrust and your drag equal each other, and you just can't go any faster. Whereas a jet engine will not lose a lot of its thrust as it increases speed. If it produces 50 pounds of thrust static on the ground, it gets moving through the air, it'll continuously produce around 50 pounds of thrust. It does start to fall off, but it's not anywhere near what happens to a propeller, because it's blades spinning and creating lift from those blades and creating that forward momentum through the air. So the big issue here with using this configuration, and this is what I really, really like about this. So as I mentioned before, a propeller is much more efficient at creating thrust. And so we can create thrust using a propeller driven by a jet engine, but this jet engine here is probably half the size of an equivalent jet engine that you would need to power a CriCri. So for example, the CriCris in the past have been powered by around 50-pound thrust engines that I think use about 22 to 23 ounces of fuel per minute. This jet engine here is about half the size of that 50-pound thrust engine, but with a propeller attached to it, it will create more thrust than the equivalent jet engine. So the fuel consumption on this is around 12 ounces per minute. And of course, if you watch the video I did before, 12 ounces per minute now gets me double the fuel time that I have at full power. So now I'm closer to 30 minutes of full power fuel using this configuration. And of course, when we're talking about needing that minimum 30-minute fuel requirement for the FAA, and that's really a cruise fuel, I probably have about 40 minutes of cruise fuel in reality. Maybe I could stretch it to 45 depending on how much thrust I'm getting and what my actual cruise speed is. But 40 to 45 minutes gets me within the legal range of taking off, let's say. So I can then now legitimately fly this engine and have 40 to 45 minutes of fuel on board. The other thing that I considered too is that this does use a lot of fuel, and it still burns a lot of fuel in comparison to a piston engine. So you could even have, for example, a taxi tank, which is somewhat popular on the RC side, where you actually have a small fuel tank that you burn the fuel out of prior to taking off, so that the time you spend doing engine run-ups and taxiing down the runway, that you're not burning fuel that you could be using for flight. So having the CriCri with, let's say, a 3/4 of a gallon taxi tank, for example, that you would have to burn that fuel off before you took off, would then make sure that when you did take off that you still had that 40 minutes, 45 minutes of cruise fuel, and that you didn't burn through a gallon of gas because you were just trying to maneuver around the airport. So that's another option too. Let's talk about maintenance, because as I mentioned before, maintenance on these things is high. Every 25 hours, this engine has to be sent back to the manufacturer or back to an authorized repair center, and the bearings have to be replaced in it. It has to be inspected, and it has to be sent back out. Now, yes, that's a drawback, because you do have a $550 cost every 25 hours of use. Now, what's more aviation than doing a full teardown, inspection, and rebuild of your engine every 24 hours and sending it back? So that basically says that every 25 hours I get a rebuilt, remanufactured engine, or at least an engine that's been inspected and looked at to be in flight-worthy condition. So to me, yes, it's a negative in cost, but I look at it as a benefit from a maintenance standpoint. I'm able to have somebody every 25 hours tear down this engine and look at it. So the cost is obviously a concern, but if you look at the cost of fuel, which is 6 gallons of gas, you look at the cost of the turbine oil, which is actually quite expensive and has to be mixed with the gas at 3 to 5%, and you consider the maintenance cost per hour, you're still, with 2 engines on a CriCri, under $100 per hour of cost. Now, that's a lot when you consider what a CriCri is and what it's intended to do, but when you look at cost of airplane rentals and things like that, it's $100 an hour is not an outrageous amount, especially with something like this that you're only going to fly around for 20 to 30 minutes anyway. So you'll get a lot of use out of this, in my opinion. I mean, if you're doing maintenance every 25 hours and your typical flight time is 20 to 30 minutes, you're really only sending us out to be rebuilt every 50 flights. And I don't know how often I'm going to fly this, but it may not be once a week, or maybe a couple times a month or several times a month at a time. But I'm looking at these rebuilds possibly only being every year. So anyway, I don't consider the maintenance an issue other than from a cost perspective. But if you're into aviation and you just listen to what I just said and it's sunk in or not, let me spell it out a little bit simpler. I can fly a twin-engine turboprop and log twin-engine turboprop time at less than $100 an hour. So think about that. The fact that I am getting a legal 40 to 45 minute flight time out of a twin-engine turboprop aircraft for less than $100 an hour. How much are you going to pay to rent a twin-engine turboprop if you actually wanted to log twin-engine turboprop time? And we can talk about whether or not logging twin-engine time on a CriCri is valid or not. I just thought it was interesting to look at the fact that I can log twin-engine turboprop time at less than $100 an hour. The other reason that I'm doing this is because nobody's done it before. That's probably one of the major factors of why I'm doing this, because I thought I want to go gas on my first build because I want it to be as close to the original designer's configuration. If I went with electric, I'd be trying to figure out how to get batteries in there and doing all kinds of things that might modify the internals of the aircraft. And I wanted to be able to make a fuel tank for this, a fuel tank mold, so that I can sell fuel tanks for people who do want to stick with the gas-powered aircraft. So my first aircraft, I did want it to be gas-powered, and I thought this is a perfect opportunity to install a turboprop on a CriCri for the first time. So one of the other things with this is weight. So for people who have installed the jets on a CriCri in the past, one of the issues has been is that this jet engine itself is extremely light. I think 5 pounds, I think is all it weighs. I think this whole thing weighs only like 7.5 pounds, I think it is. But anyway, the jets are so light that when they put the jets on them, they had to put a lot of weight in the nose of the CriCri to weigh it down. So I'm not losing anything by adding the complexity of the secondary turbine, this gearbox, this propeller, all of this stuff on here. It's adding weight, which I actually need on a CriCri, so that I don't have to put a lot of weight on the nose. Now, I'm probably still going to have to put some weight in the nose. We'll have to see. I'm trying to balance it out with some batteries and some other things and put as much of what is needed for the engine and the engine management controls into the front of the airplane, so that I limit how much extra weight I'm going to have to put in it. So that's the other benefit, again, of going this route, even though it may seem like a negative that I'm adding this complexity. So the other big negative, though, exhaust on this is a problem. Exhaust goes out both sides, and the guys who have done it before with the jets, they've had the jets just shoot the thrust directly backwards, and that seems to be okay. I think some people may have even lengthened the engine mounts slightly. I'm not really sure. So obviously I can't have, if this is my left engine, I can't have exhaust coming out the right side of this engine right into the canopy, or flowing right back into the canopy. So I have already investigated actually rotating this exhaust 90 degrees and having an exhaust that comes out the top. And then I'm going to combine the exhaust that comes out the bottom with the intake underneath, where it's going to be hidden, and the exhaust coming out the bottom will actually come out the center in the back. So I think that's a really good solution for this. Obviously I've got to design an entire engine mount and a cowling for this to work, but I've already done some CAD work on it and have come up with what I think is going to work out to be a good solution, with ducting the lower exhaust out the back and having the upper exhaust here come out the top. So I think that's going to be a good solution. I have not at this point run this engine. I'm probably going to run it tomorrow, and I will actually find out exactly what the thrust is by this 5-blade propeller. This is actually a 24-inch diameter propeller with a 24-inch pitch. It's a 24 by 24. It's actually commonly used on the PC-21 models. This could probably benefit from a better propeller, maybe even a longer propeller, but I'm going to find out tomorrow when I run this and actually find out what RPM this propeller is running at. That's one of the reasons I got this. It's an laser RPM gauge that I've attached a reflective tape on the back side of the engine here, so we're going to check the RPM at full power. I've also got on here a strain gauge or a weight gauge attached to the back of this, and this mount actually slides. It's on heavy-duty ball bearing drawer rails, and so it will pull force onto this measuring device where I can actually measure the thrust that this is actually putting out. So we'll get to see exactly what the thrust is also, and I'm going to include that in this video, so you'll get to see that later in this video. I've got everything set up here to run, so it's just a matter of taking it outside and starting it up. So let me just show you around here the engine stand setup that I have, and the configuration of the controls here. So one of the things we also have to talk about when we talk about a CriCri is throttle controls. So throttle controls are a little bit of an issue when you're dealing with an ECU or FADEC type of RC environment, because it's expecting a throttle signal from a receiver in the airplane. And what we have to do then is figure out how to create a throttle control that will emulate the signal of a servo and operate the throttle on the ECU. So one of the things I did actually a couple years ago is I created this. So what this allowed me to do was have a power connection here that would provide the 5 to 6 volts needed to emulate the servo, and then it would send the throttle signal out here to the ECU. And simply by rotating this potentiometer here, I could do throttle control. And then on the back side here, there's actually a switch that was used for the trim high and trim low, which are the two requirements needed by the ECU here. The trim high, trim low is actually what it uses to arm the engine so that you can start it, and then when you turn the trim low, it actually will shut the engine off. And then, of course, we've got the potentiometer, which just does 0 to 100% throttle. And I created this a couple years ago, and this just uses a 555 timer circuit. This is actually available as a schematic on the internet. That's where I found it. I just modified it and added the switch to be able to do the trim high and trim low, which I needed for this circuit. Now, I tested this with this engine, just with the ECU, not running, and I ran into some big problems with this circuit. It worked fine. However, because the amount of signal change between the trim high and trim low and the signal change between 0 on the potentiometer to full throttle at 100 gave me a variation of ranges of signal emulating a servo that honestly the ECU did not like. I was actually able to go from 0 to 100% on the potentiometer. Actually gave me more signal to the ECU than it wanted, and it confused the ECU to where to do high trim to arm the engine. I was able to start the engine, but then I couldn't turn the engine off because I was outside of the range of microseconds of signal that the ECU was expecting. So I found limitations right away to this, and I could have used this, but what I would have had to have done is created a stop on the potentiometer to prevent it from turning too far down and also turning too far up. So I would have had to have done some mechanical things to limit this to make this function properly and work. Now, one of the things my brother mentioned is he said, well, why don't you just use an Arduino? And even 2 years ago, I had thought about using an Arduino instead of this. But at the time, I thought, well, an Arduino is a complex microcontroller. Why would I want to use that? That's too much. I just thought, well, an Arduino, that's just too much of complexity. I don't need to add in programming and all that kind of stuff when I can just create a circuit that does what I need to do. The big problem with this is this cost me about $17 to make. An Arduino costs a few dollars, literally. And Arduino actually has servo emulator libraries already built into it. So I was able to, with this, I actually created a circuit underneath. It's actually just plugged in with a breadboard. But using an Arduino that's about the size of the tip of my finger, about from here to here, I was able to use an Arduino and program it to emulate exactly what this did, with a switch providing high and low trim and with a potentiometer providing 0 to 100% thrust. Now, the big benefit of using the Arduino is it's all programmable. So if I wanted to change how much my switch produces in signal when it's off compared to when it's on, it's programmable. I just tell it how much of the travel of the actual 0 to 100% do I want to allocate towards the trim switch. And then, of course, even with the potentiometer, I can program exactly what signal level it starts out at 0 and how high it goes to when it hits 100%. And one of the neat things about the KingTech ECU is that it actually will show you on the display here exactly what your signal is coming through as, and it tells you in the manual exactly what signal it's expecting in microseconds. So it will tell you, well, you need to start out at 900, let's say, microseconds, and when you flip the trim switch, it should go up to 1200, and then from 0 to 100% on the potentiometer should be, up to 2200 microseconds, for example. I'm just using those as an example, but what I was able to do is, as you use the Arduino, you can actually get it to be exactly what the ECU is expecting, because it's all done with programming. And it was actually quite simple to do. I'm so glad that I went that route. So what I've got here is, underneath here is an Arduino that's programmed to act as a throttle control device. I've got a high and low trim switch, which this arms the engine, which allows me then, using the throttle, which I'm actually just using a sliding potentiometer, I'm able to start the engine, and then when I want to shut the engine off, I can just turn the switch off and the engine goes off, and I have my 0 to 100% on the throttle here. This is actually kind of cool because what this did is, and I am going to use this sliding potentiometer in my aircraft for each one of the engines, and I'm going to mount 2 switches next to each other, one from the right and one for the left engine, just in this exact same configuration. But originally I was thinking, well, I'll do a mechanical throttle lever connected to some fittings and connected to some cables, and run a cable to a potentiometer that's got an arm on it that I can then use the mechanical throttle lever to control the potentiometer somewhere in the nose of the airplane. But that's a lot of complexity. We've got cables and linkages and throttle arms and all this kind of stuff that we have to make. And I thought, well, why not go straight to 100% electric controlled throttle? And I get the travel on this is over 3 inches, and the travel on the throttle arm was only 3 inches in the CriCri anyway, so I get the same amount of travel with this. And the other thing is this is really probably where I would go if I was doing electric powered CriCri, as I would do a potentiometer, sliding potentiometer, and I've seen this on other aircraft also, CriCris for example. The 4-engine CriCri actually had 4 of these sliding potentiometers next to it if you find the picture on the internet. But to me, this is a great solution. I'm just going to attach a knob that I'll make on this. I'll have the 2 throttles here next to each other, and I'll be able to slide to get exactly the throttle position that I need. So this eliminated a lot of complexity as far as mechanical linkages and cables and all the things that I would have had to have done to, do a, get to a potentiometer anyway. So anyway, that's what I'm doing here. This is emulating exactly what's going to go in the airplane. The only thing I have to do is what's underneath here is a breadboard that's got, a light and some diodes and some resistors and a few different things that are required to make the Arduino work. But I'm going to actually create a board that the Arduino will mount on similar to this, so that I can package it as a device that can be mounted in some kind of enclosure similar to how their ECU is here. So anyway, I've got everything here. This is the battery for the engine starting and the running of the engine that's plugged into the ECU. We've just got a fuel pump connected to a fuel tank here, and then I've got the vent for this fuel tank actually connected to a 5-gallon can underneath there of diesel fuel. And the reason that I did that is I need to be able to test exactly what the fuel flow is of this engine. And I'm not doing it to try and redefine what the fuel flow is. I'm trying to verify that the numbers that are in the manual for what the fuel flow is on this engine is within reasonable range. And so what I'm actually going to do is once I get the engine running here, we're going to get it warmed up, and then I'm going to go to full power on the engine. And because this tank is vented to the 5-gallon can, as it uses gas out of here, it sucks gas into this, so it keeps this tank full. So what I'm going to do then is while this is running at full power, I'm going to pull off this line here going to the 5-gallon can. That will open up this vent, and what it will do is it will only draw the fuel out of this. And so what I'm hoping is to be able to draw all the fuel out of this and time exactly how long it takes for that engine to empty this fuel tank, which I've calculated should take about 2 minutes and 40 seconds. 2 minutes and 40 seconds means that the manual is accurate, or at least close to accurate, of what the actual full power fuel usage and fuel consumption is on this engine. I have to verify that before I can say 100% I can use this on a CriCri. The other thing I mentioned too is I've got this scale here, which will tell me exactly what the pounds of thrust is being created by that particular propeller in this engine configuration, and it should be higher than 50 pounds. I'm hoping it could even be upward of 70 pounds of thrust, but we'll find that out. And then as you see here on the back side of the spinner, I just attached a little piece of reflective tape so that I can use this to actually check the RPM of the engine at full power, which should be in the 5,000 range, ideally, if that propeller is pitched properly for this engine. Those are the two things the three things I'm really trying to figure out and test here: is the RPM of that, the pounds of thrust, and the fuel consumption. If I can verify all three of those, then at least I have an accurate way of verifying that this engine is really going to work and how well it's going to work on a CriCri. So that's what we're going to do next when we start this thing up and see how it runs. So I was able to do 2 test runs on this engine to try and verify some of the information I mentioned that we were going to try and collect on this engine. The first thing was the fuel consumption, to just verify that it was close to what the manual specifications are for the KingTech K100. And we also wanted to test the pounds of thrust developed by this propeller. And I also wanted to check the RPM that this propeller reached in static configuration at 100% throttle position. So most of those tests went as planned, some didn't. I had some issues with the fuel consumption test. As I mentioned, my plan is that I've got this 1,000 milliliter tank here that's connected through a vent line to a 5-gallon can underneath the bench here. And the idea is to start the engine, get it warmed up, get it up to 100% power, and then disconnect the vent line here to open up the vent to this tank so it would draw the remaining fuel out of this tank, and I could measure in time exactly how long it took to empty this 1,000 milliliter tank. Now I can't pull these vent lines off. I mean, it's hard enough to get these fuel lines on. They're impossible to get off. So what I did is I just got a pair of scissors and I just cut the line, which disconnected the tank below, and then I had my cell phone and I was timing how long it was going to take until the engine started to sputter. Now, I was concentrating on cutting the line and getting that timer started. That I cut the line, I started the timer, I was watching the timer, it was like 6 seconds in, I think. And I looked back over at the tank, and the tank's a third empty. So I'm like, what in the world just happened? Because I was looking at that tank before and I didn't see a lot of air in it. Yeah, there was a little bit of air in the top, kind of like there is now. But all of a sudden, a third of the gas was gone within a few seconds. And I thought, whoa, what's going on here? Where's this fuel going? And is this really off this much? Because obviously this isn't usable if I can't get a minimum amount of time out of it. So I let the timer run. The timer ran actually to 2 minutes. And then the engine started to sputter because the clunk line inside the tank started drawing air inside of it. And of course, there was still a little bit of fuel left in this tank at that time, but it did run for 2 minutes. And considering that from my visual perception, that tank was already down a third of the tank. And I think I'd mentioned before that in order for this calculation to work out, this engine needed to run for 2 minutes and 40 seconds to get to the point where it was emptying this tank. Now what I did is I was glad that I had a video of all this, because I was able to go back and look at the video and see what happened. So what had actually happened is that this fuel pump for the jet engine was pulling so much fuel out of this tank that the vent line was not really able to keep up with siphoning it out of the 5-gallon can. So what had happened is this tank here had so much vacuum in it that it started to collapse. If you actually look in the video, I'll show a picture, all four sides of it were just sucked in. And so what happened is as soon as I cut this vent line, of course the tank blew back up to its normal size, but of course there wasn't that amount of fuel in the tank. So immediately it went to looking like it was only 2/3 full, which it was. So it wasn't a scientific method of figuring out exactly the fuel consumption, but honestly it worked fine, because the fact that I got 2 minutes out of what I perceive as between the fuel that was left in the tank and the fuel that was missing, that it only burned through 2/3 of a tank of gas in 2 minutes, and I was expecting 2 minutes and 40 seconds for the entire tank, and a third of a tank would have been more than 40 seconds. So I'm happy with now saying that the specs that are in the manual for the KingTech for this engine are accurate enough for me. In fact, I'm looking at that as being the worst case scenario, because I think I actually did better than that. Now, the reason why I wanted to check that number is because the numbers in the manual were off. And I want to say they're off. Their calculation, they had two numbers in there, which was grams per minute, and the other one was ounces per minute. And the ounces per minute for the K40, the K60, and the K100 turboprop versions were all the same, which didn't make any sense. And of course, I figured out it was actually the K60 numbers that got copied to the other ones. But anyway, so it was also confusing to me that they were doing calculations for fuel in weight, in grams and ounces. And of course, I thought, well, maybe initially the ounces were actually fluid ounces, not actual weight ounces. But of course, if you go back and do the calculation between grams and ounces, it's obviously weight, because that's what the calculation comes out to be. And believe it or not, the calculation for fuel consumption in ounces and weight is actually not that far off. In fact, on a 30-minute fuel burn, your only difference is about 2 minutes. The fuel consumption at ounces of weight per fuel is actually about 2 minutes less than the equivalent calculation with fluid ounces. So it was all a little bit fuzzy to me on exactly what was really accurate and what wasn't. So the end result is the numbers in the manuals are all based on weight. It's obvious, it would say fluid ounces if it was fluid ounces. So, and the calculations work out to be equal to weight. Now the other thing that was confusing too is this engine will actually run off of 3 different fuels. It will run off of kerosene, it will run off of Jet A, and it will run off of diesel fuel, just regular pump gas diesel fuel. Now the diesel fuel is what's recommended on this engine. So I wasn't sure if that's what they were using for their calculations, because Jet A actually weighs almost a pound less per gallon than pump gas diesel fuel. That's obviously a big difference in calculations. So I have to just assume that they're using pump gas diesel fuel for their calculations. That's working out to what I'm calculating here. That's the recommended fuel, and it's the preferred fuel for maintenance purposes that seems to run this engine better, provide a little bit more power, and is better on the bearings. So I'm assuming that's what they're using. So the end result is I think we're good with gas. Now if I recalculate everything back again from using a 51-pound thrust jet engine, for example, on the CriCri compared to the KingTech turboprop, assuming that the calculations are correct using diesel fuel and using fuel consumption and weight, what I came up with is that the fuel consumption of a 51-pound thrust pure jet engine that has previously been used on the CriCri, normally it's been JetCat or some other brand other than KingTech, but the fuel consumption would have been at full power burning 6 gallons of gas on a jet engine in 14 minutes, not 16 minutes like I had thought before. Now what that did is it actually lowered the numbers on this a little bit too, because the full power fuel burn on this for 6 gallons of gas is about 26.8 minutes. If I assume that 75% power, which would be 75% fuel consumption, would be equivalent to a reasonable cruise speed, I'm at 36 minutes to burn 6 gallons of gas. So that's still reasonable. I was hoping for it to be 40. I was hoping I could calculate it to get to 45, just something more, but honestly 36 minutes is fine. I think there's other things that we can do to either alter the numbers or alter the amount of fuel to give us a little bit more time. Even the taxi tank, like I said, is almost a must in this situation. The other thing that's kind of good about the lower times of available usage of the CriCri is that I often wondered if we went full electric, what would our flight times be under that scenario? Would it be less than with this KingTech turboprop? Would it be equivalent? Would it be more? I would assume it would be less, but I'm not really sure. And that's one of the things that I think this will tell me exactly what is going to be a reasonable flight time for this aircraft, and if 20 minutes of flight time or 15 minutes of flight time is reasonable to get up in the air, do some stuff, and come back down, or is that just not enough time to get anything done? I'm not really sure, honestly. It'll be interesting to see. Now, the other thing, too, though, is the CriCri, I'm building it because I want to do aerobatics. That's one of the primary things I wanted to do with it. We are not supposed to fly aerobatics in a CriCri on a full tank of gas. You're supposed to burn off some fuel, then you can do aerobatics at a certain fuel level because you've reduced the weight of the aircraft. Obviously, if we were using batteries and we're operating at gross weight on takeoff, we're not losing any weight. We're not losing any weight as we fly because we're not burning anything. So it would be interesting to know, what the solution would be using a battery-powered aircraft if we were putting enough batteries in, or needed to put enough batteries in to reach gross weight to get long enough flight times. Are we still able to technically do aerobatics, or do we have to be careful with what we're doing so we're not overstressing the aircraft because we still are operating aerobatics at gross weight? Those are all things that I'm going to have to figure out down the road, and it's also one of the reasons that I went with a gas-powered engine initially, because again, there's a lot of what-ifs on the with the battery possibility and electric power. The other thing is dealing with the FAA with electric. I wasn't exactly sure what issues I would run into with them on either proving flight times or proving battery drainage and usage and weight and all of those other things. So those are all things we're going to get into the future, but for now, I think I'm happy with this. I think it's going to work good. So let's go on to the other statistics. The other two things I was going to test was thrust with this prop at full power, and also the RPM of this prop at full power. So static RPM, which is critical in understanding exactly if we've got the right size propeller or not. If we're at very high RPM with a propeller, it indicates that we probably should have more pitch, have more prop that we're turning because we're actually wasting power. If it's too low, it indicates that we got too much prop. We're pulling too much thrust initially. We're not letting the engine get up to its optimal RPM when it's running. And the optimal RPM for this is 5,000 RPM static, and that should unload up to 7,000 RPM in flight. And so what I calculated here, and I was able to verify this on 3 different occasions with 3 different tests on the thrust, I was getting a very solid 63 pounds of thrust with this propeller and this engine at full power. At that 63 pounds of thrust, the propeller itself was turning at exactly 4,900 RPM. Now that combination is pretty good. I knew I needed to be over 50 pounds of thrust for sure. I was hoping to be close to 70 pounds of thrust, but I honestly didn't know. So coming in at 63 pounds of thrust, solid, repeatable, with this and the fact that the propeller was only turning at 4,900 RPM, not 5,500 or somewhere over that. What it means is I've got a lot of RPM left. If we go up to 7,000 RPM, I've got 2,100 of RPM available to me that allows for this prop to unload and continue to provide 63 pounds of thrust up until it reaches hopefully its maximum 7,000 RPM. At least that's the goal. So I'm very happy with the test that I did, and of course if you want to see this engine run, I'm posting that in another video because I wanted kind of a first time KingTech K100 start up and run video separate from this. The engine ran flawlessly. I mean, all I did with this engine prior to starting it up is I did follow the manual's procedure for just priming the lines. So just getting fuel into the lines, which was just disconnecting the fuel line from the engine and going into the ECU and turning the gas pump on and just pumping fuel out the other end and then hooking the fuel line back up. Started flawlessly, started all on its own, didn't sputter a bit, ran throughout its entire power range back to idle from full power all back to 0 with no issues at all, nothing. And I know I would not have had that ease of start and run time if this was a 2-stroke. So very happy with that. Let's see, the other thing I was interested in figuring out with this is how hot the exhaust was going to get. That was one of my biggest concerns about using this on a CriCri is, I'm thinking, is there 1,250 degrees Fahrenheit coming out of this pipe right here? How hot is this? Can I get anywhere close to this? Do I have to stand 3 feet away, 6 feet away? How much heat is coming off this thing? Because nobody really tells you when you're looking at buying one of these. You really have no idea what you're dealing with. So what I was very pleasantly surprised with is, of course, with this prop turning, it's blowing the exhaust back. Even though the exhaust is coming out the side here, it's blowing back. I was able to put my hand right here with the exhaust blowing straight back because, again, it's not coming out. You could hold your hand here and you weren't feeling it because the prop was pushing it back. I could hold my hand within 10 inches, and honestly, it was hot, but not like burning hot. I could have held my hand there forever. It's just really, really hot air. That's it. So I wasn't really concerned then about, oh, am I going to melt the canopy on this airplane, if the exhaust is blowing the wrong way. No, it really isn't an issue from what I can tell at all. It is an issue, though, from the exhaust standpoint, because the amount of exhaust that comes out of this, especially during startup and engine run, it's a lot of fumes. So definitely routing the exhaust to keep it far away from getting anywhere inside the airplane is going to be a bit of a task. I got to make sure that there's no exhaust leaks coming inside of that airplane, because the amount of exhaust that comes out of this thing it's a lot. I was completely covered in diesel fuel and turbine oil smell when I got done running this thing, especially because I was standing right here running it from the control box. So again, very happy with this choice. I think this is going to be a fun thing to do with a CriCri. Like I said, how long this will run or will be used in that configuration will be determined by how reliable it is and what issues I have with reliability and also with flight time. So I'm not concerned about reliability with this. I realize what this engine is. I'm going to be very happy if it lasts at all, to be quite honest, because I'm using it for something it's not supposed to be used for. And so I will not hold KingTech accountable for the fact that this may or may not hold up under what I'm trying to do to it. I will, this is going to require a fair amount of maintenance, and probably more maintenance than anybody has on the RC side. I don't know if this engine in total have to be replaced every 100 hours because we've worn out the gearbox or worn out other parts of it. I honestly don't know, but it's not going to be a high-hour aircraft anyway. So this is just a fun. Let's do this to see if we can make it happen. So anyway, I think that's it for this video.